Hello everyone. This is the first pre-recorded lecture for this course on electrodynamics. So before we go into a detailed discussion about Maxwell's equations, or before we dive into the physics, let us quickly recall some of the mathematical preliminaries that will be very useful in our discussions. So let us begin this first lecture with a few mathematical preliminaries. I'm sure all of you have mostly seen the things that I'm going to say today, but it will be very useful in our discussion, and also I'll take this opportunity to set up the notations so that different books and different references usually have different notations. But I will set up my own notation, and here I'll lay it down, what my notation will be. So the first thing that I want to talk about, and which I'm sure you all know, is the so-called Dirac delta function. And the definition of the Dirac delta function, which I'm going to denote by this delta of x, is given in the following way. So the definition is as follows. So if you take any other smooth function f of x and multiply it with the delta function and integrate from minus infinity to plus infinity, what you get is f of 0. So this, if you like, is the definition of the delta function. So here of course, you can generalize this immediately to this statement, which is slightly more general. So that if the 0 doesn't occur at x equal to 0, but at x equal to a, let's say, then you get f of a. Okay, where a is again any real number. So basically, the Dirac delta function is a blip at 0. So it's 0 everywhere, but it's non-zero at x equal to 0. And when its arguments vanishes, it clicks and it gives you the corresponding value of the function f of x for which its argument vanishes. So you get f of a here. So this is the case if you were in 1 dimensions. Similarly, you can define a very similar object in 3 dimensions, and that object would be written in the following way. Let's say you have a scalar function f of x vector now in 3 dimension. Let's say this scalar function is a function of x, y, and z. That's what I denote by x vector. And now if you have this delta function x minus r vector, where this r vector can be any constant vector, any other constant vector, and you integrate it over the whole volume d cube x, then this will give you f of r vector. So this is the 3-dimensional generalization. And often in many references, you will see that they put an index 3 out here on top of the delta function. This just denotes that it's a delta function in 3 dimensions. But I will try to avoid doing that. Okay, so I will just not write this 3. And the dimensionality of the delta function would be clear from its arguments. So whenever its argument is a vector like this, then we are talking about the 3-dimensional delta function. Okay, so this is going to be my convention, and so now the delta function has very, very interesting and useful properties. They have several interesting properties. Some of them I'll give you in your problem set to prove. But let me write down a couple of them. So properties. The first one is if I have delta of x delta of minus x, this is just equal to delta of x. Okay, so how do you see that? Very quickly. So you can see that by the following way. So again, let's just use its definition. So if we first say that if we integrate some function, let's say from minus infinity to plus infinity, f of x delta minus x dx, then we can always do, if we want to go back and use this definition out here, so we can change x to minus x in this definition. And if I change x to minus x, it's kind of very simple. So what you're going to get is minus infinity to plus infinity, f of minus x delta x, and here you will have d of minus x, or let me write down minus d of x. So right, so now this minus sign is going to, so basically when you do the change of variables, you will have this integration limits would also flip. So you will have here minus infinity to plus infinity, sorry, infinity to minus infinity when you do the change of variables, and this minus sign is going to revert it back. So you are again going to have minus infinity to plus infinity integral f of minus x delta of x dx. So this is, as we know, would again be given by simply f of 0. Okay, so this will be given by f of 0. So because x equal to 0 is the corresponding value, so this is going to be given by f of 0. So similarly, if I use the delta function instead, minus infinity to plus infinity, f of x delta x, then by definition this is f of 0. So these two delta functions, delta of x and delta of minus x, have the same property. So if delta of x has this property, then delta of minus x also has the identical property, that it gives back f of 0, and therefore we can say that delta of minus x is equal to delta of x. All right, so the second property, which is interesting, is basically the fact, if now we have some real number alpha times x, then this is simply given by 1 by mod of alpha delta x. Okay, so you can try to prove this second one also in exactly the same way. So just assume that either alpha is greater than 0 or alpha is less than 0, and from that fact you will just have that in both the cases you will have this, the mod sign comes out of that consideration. Okay, so here let's proceed further. So again, I'll give you some more exercises with the delta function in your problem set, so that you have some practice. Now let's try to do the next thing, which is so let me use a different color here. That's your Dirac delta function. The next thing that I want to talk about is Fourier transform. Again, I'm very sure all of you are completely familiar with this idea of Fourier transforms. And, I'll just mention it just to lay down my notation. So, or my conventions here. So basically, if I have a function, again for 1D, if I have a function f of x, then its Fourier transform would be defined by this integral, let's say minus infinity to plus infinity dx, minus infinity to plus infinity dk, f tilde of k e to the power I k x. Okay, so this is my convention, and I want to put in the factor of 2 pi here. So the inverse Fourier transform f tilde of k would be given by, without any factors of 2 pi, minus infinity to plus infinity, now dx, f of x, but e to the power minus I k x. All right, so this is going to be my forward Fourier transform and backward Fourier transform. In some textbooks, you will see that there's a 1 over root 2 pi here and 1 over root 2 pi here. But in my conventions, I'll prefer to keep the 2 pi factor intact, and I will keep it in the forward Fourier transform. Okay. So, right. Now, similarly, this can immediately be extended into 3 dimension, which will be our interest. And here, if you have a scalar function, let's say f of x vector, I can write this down as integration over the whole volume. This I am representing as minus infinity to plus infinity. The integration over the whole volume d cube k f tilde. Now this is also going to be a k vector e to the power I. Now it's going to be k vector dot x vector. Okay. So that's going to be the thing. But now for the factors, I will have 2 pi cube because it's 3 dimensions. Okay, I'll have 2 pi cube. Similarly, the inverse Fourier transform, I will not have any such factors. I will just integrate minus infinity plus infinity over the whole volume. Here I integrate over the whole volume of the k space. Here I integrate over the whole volume of the position, physical x space. So this is going to be d cube x f of x e to the power minus I k vector dot x vector. This is going to be my convention. Okay, very good. So with these 2 things in place, what I want to do now is to write down immediately integral an integral expression for the delta function. So let me just from the consistency of these definitions, I can write down an integral representation of the delta function. How do I do that? So basically what I want to do is take this definition of f of x, take this definition of f of x and plug it back in here. Okay, so I want to take this and put it back in here. Okay, let's try to do that. So if I try to do that, what will I get? So from the first definition, I will have f of x is equal to 1 by 2 pi integral minus infinity to plus infinity dk. Now here I'm going to put in this definition here. So this definition is minus infinity to plus infinity dx, the same f of x which appears here on the right hand side, on the left hand side. It's the same f of x e to the power now minus I k x. Okay, again, so this is the integration variable. So if I don't want to confuse this integration variable x with my x out here. So what I'm going to do is I'm going to use a different integration variable here, Okay, and I'm going to use, let's say, y. Okay, so basically what I've done is just taken this fx, this definition, and plugged it back in here. Okay, I will also have this factor of e to the power I k x. Okay, so very good. Now this k and y integrals are independent, so I can, take this y integral outside and the k integral inside, and I can rewrite this function in the following way. I can write it as minus infinity to plus infinity dy f of y, but now within bracket I can write 1 over 2 pi integral minus infinity plus infinity dk e to the power minus I k right, or plus I k, let's say, e to the power I k x minus y. That's my definition, x minus y. So I'm just combining these two exponentials here, and so that's what I have. Okay, I've written everything here. Now I want you to compare this expression with the expression for the definition of the delta function. So for the definition of the delta function, I could have written that this is some d of y, f of y, delta of x minus y. Okay, so then this would have become f of x. Now if that is true, then I can identify the delta function here with this integral here that I have within bracket. So I can write that with this I can write an integral expression for the delta function, which is delta of x is equal to in 1 over 2 pi minus infinity to plus infinity dk e to the power I k x minus y. Okay, so with this so this was again in 1 dimension. Similarly in 3 dimensions also I can have a definition for delta of x vector is equal to 1 by 2 pi, but now it will have all the 3 factors of 2 pi. Now this is again a volume integral, which again I'm denoting from minus infinity to plus infinity. So this is a volume integral over the k space, d cube k. I'll not put the vector here, d cube k e to the power I. Now this is k vector of x vector minus, let's say, x vector, k vector, x vector. Right. Here, right. So if I literally identify this, I should have written this as delta of x minus y. Okay, if I identify this, again going back, if I identify this with this, then I should really write x minus y. If I have x minus y here, I can again put y equal to 0, so delta x becomes e to the power I kx here. So similarly here for 3 dimensions, delta x vector is e to the power I k dot x vector. But again, if you have x vector minus r vector, then here also x vector minus r vector is going to appear. Okay, if you have delta of x minus r vector like this, then here you have to write e to the power I k x vector minus r vector. All right, very good. So now so that was more or less what I wanted to say about the delta function and the Fourier transform. But now the third thing that will be very important in our discussion is this we'll need not only a little bit of, but I think we'll need a lot of vector calculus. Okay, so we'll need a lot of vector calculus. So just let's brush up our knowledge on vector calculus. So of course, if you remember, you can have, for instance, a scalar field, something called a scalar field, phi of x vector. This is how I'm denoting a scalar field. And this, essentially what I mean by this phi is a function of the coordinate x, y, and z. Okay. So, and similarly, there's a vector field this I denote with an arrow, a vector, x vector. And what I mean by this is the following, that this is equal to, let's say, a1, which is a function of, again, x, y, z, I, the unit vector along the x direction. I'm using, again, just to mention here, I'm using Cartesian coordinates. So throughout this discussion in this course, we'll be in flat space. And so we are going to use Cartesian coordinates as far as the space part is concerned. Again, when we go into relativity, I'll give you a separate discussion of the Minkowski space. But until we go into a relativistic discussion, this is going, we are going to stick to, this Cartesian coordinates in flat space. Okay. So basically, there are x, y, and z direction which are mutually orthogonal, and the unit vectors along these directions are denoted by I hat, j hat, and k hat. And I am writing down all my vectors in terms of these Cartesian coordinates, x, y, z, j hat plus a3, x, y, z, k hat. Again, at some point, I may need a little bit of spherical polar coordinates or cylindrical polar coordinates. But when I need them, I will develop, what they are, whatever I need, I'll develop that. But for most of our discussions in this course, we'll try to stick to the Cartesian coordinates and, keep life as simple as possible. So this would be a vector field. This is the expression for a vector field, and with the scalar and vector fields now, you can define various kinds of derivatives on them. So the first thing that you can define is a gradient, and the gradient is essentially you act with this gradient operator on a scalar field, and as a consequence you get a vector field. Okay, and what is the definition of that? The definition of that is, this is I hat del x phi plus j hat del y phi. Again, phi is a function of x, y, and z, and k hat del phi del z. Okay, this is the definition. Okay, so similarly, so before going and defining the divergence and the curl, let me give you a little bit of notation here. Okay, so the notation that I want to introduce here is as follows. So as far as the coordinates are concerned, let me mention it. So as far as coordinates are concerned, this is a notation. This is very important. Okay, I'll write it with red. Okay, this is notation. Okay, I'm not discussing any, tensor calculus or any such thing. I'm just giving you a new notation for things which you already know. So this is coordinate, sorry, wrong color. So this is coordinate. Usually you are used to denote it with this x, y, and z, but I'm going to denote these Cartesian coordinates as x1, y1, sorry, x1, x2, and x3. Okay, I'm going to denote it in that way. And so that's the first thing. So if I do that, then what I'll get is, if I want to write down the nabla operator, this I will write as I hat del del x1, right, plus j hat del del x2 plus k hat del del x3. Now this, I'm going to use a shorthand notation for this, and I'm going to write this as I hat del 1 plus j hat del 2 plus k hat del 3. This is again going to be my notation. Okay, so under this notation, I can simply write down the gradient. Since I've written it there, let me rewrite it. Under this notation, I can write the gradient as, so this A vector would be given by grad of phi. This is equal to I hat del 1 phi plus j hat del 2 phi plus k hat del 3 phi. That's going to be my notation. Okay, so very good. That's the notation. But now let's get back again to the various derivatives that we are defining. The second thing that we can define is the divergence of a vector field. Okay, so if we take the divergence of a vector field, then we get a scalar. So a scalar field can be obtained by taking the divergence of a vector field. Okay, sometimes people put an arrow over nabla. Again, I'm going to avoid doing that, because nabla is a it's very clear, what I mean by this. It's this thing. Sometimes people try to make it explicit that we are dealing with a vector by putting in an arrow here. I'm going to try and avoid doing that, again, just not to clutter notations. So basically now you can take this, and in our convention we can write this as I hat del 1 a1 plus j hat del 2 a2 plus k hat del 3 a3. Again, del 1, del 2, del 3 are basically partial derivatives with respect to x1, x2 and x3, and a1, a2, a3 are essentially functions of x1, x2, x3. Okay, just like we had this vector, we had this vector function here, this is what we have. Okay, very good. So this is the definition of the divergence. Okay, and now the last thing that we need here is the curl. Okay, so what do we mean by the curl? So the curl essentially is gives you a vector field V when you take the curl of another vector field A. Okay, now what is the definition of that? That is defined usually through this determinant. You write down I, j, k here, and del 1, del 2, del 3 here, and you say that a1, a2, a3 here, the components of the Cartesian components, and with respect to that you can now write I hat, this component is going to be del, let's see, so it's going to be del 2a3 minus del 3a2, okay, plus j hat, so this is going to be del 3a1 minus del 1a3, and the last one plus k hat, this is going to be del 1a2 minus del 2a1. So that's the definition of the curl for you. Okay, so this vector v, the various components of this vector v are given in this way as derivatives of these functions a1 into a3. Beautiful. But now so you have already known all these things, but now I want to rewrite all these things in a slightly different notation, and this may be slightly new to you. Okay, so what I'm going to, again, this is again notation, so let me write down in red that what I'm discussing is again notation So, this is nothing new or not to be, scared about. So what I'm discussing here is just notation. So the first thing that I'm going to denote is, if I have a vector field. So if I have a vector field, sorry. This vector field A, this has three components. I'm going to denote it by this A, I. You know what I mean by I, where I runs from 1, 2, 3. Okay. So, this, when I write this vector field as AI, when I'm writing this as AI, what I'm referring to are the components with respect to the Cartesian coordinates. Okay. This is very important that I'm referring to the components with respect to the Cartesian coordinates. And so basically what I mean is, this is the collection of the set A1, A2, A3. Okay, in Cartesian coordinates. Okay, so now, so if with this is the, this is the way I'm writing the vector field. So if I write the vector field in this way, then I can define dot product between two vectors or two vector fields. Let's say A dot V vector. Then I will write this as A1 V1 plus A2 V2 plus A3 V3. Right. Now this, then I can write using this, notation. This I can simply write as AI Vi. There's a sum over I equal to 1, 2, 3. Okay, I hope this is clear what I'm writing down. So this whole thing here, I can write as a sum like this, AI Vi, where, I runs from 1 to 3. Now, let me do the following. Let me introduce here let me use a special color for it. Let me introduce here what is known as the Einstein convention. And what I mean by that is the following. It says that repeated indices so these are the indices. Okay, these are the indices. It says repeated indices are assumed to be summed over and so they're assumed to be summed over. So in other words, we would not have to write this sum and carry it around. Okay, we would not have to write this sum and carry it around. So they are assumed to be summed over unless otherwise specified. Okay. Okay, so basically under this convention, I can write this without the sum simply as AI Vi. Okay, so I don't need to put this sum. Again, this is a very useful convention because this saves a lot of writing, these sigmas all around. Okay, so whenever the indices are repeated, you know that there is a sum over I from 1 to 3. Okay, this you already know. Okay, very good. So this will require a little bit of getting used to, and this is what I want you guys to get used to this convention and the way to deal with these indices a little bit in this index notation. Okay, this is exactly everything that you have done before. Again, let me emphasize that There's nothing new here, and it's just whatever you have done in a slightly different language. Okay, so this is the dot product. Now coming back to this original discussion, so I want to, let's say, now write down the gradient again. So it's the gradient. So again, the gradient of a scalar field is a vector field. So this I will, in my notation, I will write AI equal to del I phi, because this nabla, which is essentially, I can write as, this I del 1 plus j del 2 plus k del 3. This in my notation I'll simply denote as del I. Okay, and if I do that, then I can write down the gradient in this way. So I can write down the divergence now similarly. So the divergence, this is a scalar field is equal to the divergence of a vector field, and in my notation I will just write phi is equal to nabla I AI, and I don't need to do anything else. I don't need to write anything else, because again, when I have repeated indices, then it is meant that I will sum over I equal to 1, 2, 3. Okay, that is an assumption, so I don't need to write it. Okay, whenever I have repeated indices. Beautiful. Now the question is, how do I write down the curl? So the curl, again, just to remember, it is a vector field. So it is an operator on a differential operator on a vector field giving rise to another vector field. Now, how do I write it down in this notation? Okay, so if I have to write it down in this notation, then I have to introduce, a few more things here, and let me do that. So let me introduce a few more definitions here. So let me introduce here, at first, let me, again, so these are some definitions first. So the first one, I want to define something called a Kronecker delta function. We've talked about the Dirac delta function, but then there's a discrete version of it. So here this has two indices, I and j, where both I and j, let's say, runs from 1 to 3, and this is equal to 1 only if I equals to j, and this is equal to 0 if I is not equal to j. Right? So basically, this is the definition of the Kronecker delta function, if you like. And this is a very super useful quantity to deal with indices. Okay, it comes around. Okay, in particular, for instance, if I do a delta I, again by summation convention, I know that there's a sum over I, which will mean that this is equal to, the first one is I, so it's 1, delta 1, 1, delta 1, 1 is 1, plus delta 2, 2, that's again 1, plus delta 3, 3, that's again 1, so this is equal to 3. All right, so this is the Kronecker delta function. The second thing that will be again extremely useful in everything that we discuss is this symbol called the Levi-Civita symbol. Okay, now how is that defined? Now here this one had two indices, but the Levi-Civita has three indices, I, j, k. And here, as you can see, this delta ij is symmetric with respect to I and j. So if I write down delta, so let me write that down here. So if I have delta ij, that is the same thing as writing delta ji. It's symmetric with respect to the two indices. Okay. So now the Levi-Civita, on the other hand, this is defined as epsilon ijk equals to 1 for even permutations or symmetric permutations of 1, 2 and 3. Again, I, j, k, everything runs from 1 to 3, runs over 1 to 3. So this is equal to 1 if we have symmetric permutations of 1, 2 and 3. What do I mean by symmetric permutations? So I can start with 1, 2, 3. Okay, that's one thing. Then the next thing would be something like, if I do a symmetric permutation, so this will be like 3, 1, 2. That will be another symmetric permutation. So this is going to be 1 for all these things. And the next thing is going to be, let's say, 2, 3, 1. That's going to be again another symmetric permutation, and so on. Okay. So for all these, when the indices take these values, I equal to 1, j equal to 2, k equal to 3, then it's equal to 1. And similarly for these other cases as well. So this is equal to 1 for the symmetric permutation of 1, 2, 3. And for odd permutations or antisymmetric permutations, so for antisymmetric permutation of 1, 2, 3, this is -1. And what do you mean by antisymmetric permutation? So for instance, 1, 3, 2 is an antisymmetric permutation, and or an odd permutation. And so basically, let's say 2, 1, 3, that is another one, and so on. Okay. So this is equal to 1 and -1, and in all other cases this is equal to 0. So in all other cases this is equal to 0. So basically, if you have examples, so if you have epsilon 1, 2, 3, this is equal to 1. So epsilon, let's say 1, 3, 2, this is equal to -1. Now epsilon 3, 1, 2, this is again equal to 1, and so on. Okay. Now if you have any repeated indices, let's say 1, 1, 2, then it will always vanish. If any two indices are repeated, then it always vanishes. This is one thing to keep in mind. Let's say 1, 2, 2, then it always vanishes. Similarly, if 3 indices are repeated, of course it also again vanishes. Okay. So this is the structure of this epsilon, and so in general, the epsilon is antisymmetric with respect to its indices. For instance, epsilon I, j, k would be equal to minus epsilon I, k, j in terms of this abstract. So I've shifted k and j, that would give me a sign. Okay, so this is antisymmetric. It's a completely antisymmetric. So basically, so similarly, this is again going to be equal to epsilon k, I, j. Again, I get one more sign if I interchange I and k, for instance, here. Okay, so this is how, the epsilon is, and, this is how to deal with it in the index manipulations. Very good. Now, before we, go back into our discussion of vector calculus, let me also mention that there are some very interesting and important properties of this epsilon or the Levi-Civita, and particularly when you take product of two Levi-Civitas. Okay, so I will let me discuss some properties. The first one, which I think is quite important, is if you have epsilon I, j, k, if you have a product of two Levi-Civitas, L, M, N, let's say, this is given by the following determinant. So I have a delta, delta, delta. Write it as, yeah. Right. It is given in terms of the Kronecker deltas that I mentioned a while ago. So this is going to be I, j, k, I, j, k, I, j, k, and here it's going to be L, L, sorry. Going to be L, 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 N, M, M, N, N, n. You see, the sign that you get when you interchange rows and columns, compensates for the antisymmetry of this ijk and lmn respectively, the way it is arranged. And so basically it has the right symmetry structure compared to this, when I write down in terms of the Levi-Civita, this has the right symmetric structure thanks to the fact that in a determinant, when you interchange rows and columns, you get a minus sign. Okay, and the idea is that, again, so if we start with this, then we can just, so let's say this is property 1, then we can go on, making, summing over indices here. So the second thing that I can immediately write down is what happens is if I have epsilon I j k and epsilon I m n, then, from this definition, so you can write the determinant out, it's a long expression, and there if you set L equal to I and sum over I, okay, if you perform that operation, then you will see that this would reduce to delta delta j m delta k n minus delta j n delta k m. Okay, it will reduce to that. And similarly, if I do one more, like, contraction or sum over index, okay, the sum over indices, two different indices is often called contraction. So if I do another contraction, so epsilon I j k, epsilon I m, so sorry, epsilon I j n, then this would be, both these terms, you see what I have done here, set j equal to, I have set j equal to m here, right. So basically what I'm doing here is, in this expression, I can set j equal to m and sum over j, okay. So if I set j equal to m and sum over j, because j is summed over here, I is summed over, and j is summed over, okay. So I have to set j equal to m and sum over j. So if I do that, I will have a delta, what do we have here? A delta jj here, delta kn minus, this is going to become, j and m. So this is going to be the same index, delta jn, delta kj. Okay, where there is a sum over j. Now if there is a sum over j, as we saw, delta jj, this is going to be 3 delta kn minus, now if I use this fact, perform the sum over j, then this simply reduces to delta kn, because this will be non-zero only when k and n, this will be 1 only when k and n are equal, otherwise it's going to be 0. So I can write this down. Okay, this is another, if you like, this is a consequence of the definition of the Kronecker delta. So now this is going to become equal to twice of delta kn. Okay, so if you have two indices contracted, then I will have twice of delta kn. Okay, so this is epsilon ijk, let me write it down again, epsilon ijn, this is equal to twice of delta kn. Okay, so now the fourth one is, if we again set k equal to n and perform a sum over it, so I have a delta ijk and I have a epsilon ijk and I have a epsilon ijk, where both all repeated indices are summed. So this is going to be equal to twice sum over delta kk, and this is going to be equal to 6. Okay, so these are the things that follows. Now as far as the proof of this definition of this delta of this of the epsilons in terms of the Kronecker delta is concerned, okay, so this is a little bit, you have to use a little advanced notions, but essentially the point is that the object that can be written as in the following, with this following index structure in 3 dimensions, the index structure is as follows, that it's completely antisymmetric with respect to 3 indices, and it's these two are completely antisymmetric, and then if I exchange, I and L, these are, there's an exchange symmetry. So because, I can write down epsilon LMN first and epsilon IJK second, I can just interchange them, they are just, simple products. So they're just product of numbers, so I should be able to interchange. So whatever takes into account this exchange property of the indices, that object in 3 dimensions is unique. And so this also has the right index structure, and the exchange properties of the indices on the left hand side is the same as the exchange property of the indices in this determinant expression here. Now the only thing that could have not worked is some constant out here. There could have been some constant out here. It was possible that there was some constant out here, but this constant you can determine from the fact that if you perform a sum over everything for the epsilon, then you get back 6. Okay, and if you perform a sum over all these indices in terms of the delta function definition, then you also get back 6. So this whatever this constant appears here, this constant had to be equal to 1. There was no other option for it to be 1. Okay, so that's how the general argument of how it follows goes. But this expression you can try to verify yourself by putting in various values of 1, 2, 3 for the indices and checking whether this expression is right or wrong. You can even try to write down a code or a computer program, a very small little computer program which verifies this expression, and then taking this as your starting point, you can immediately show 2, 3 and 4 follows from this starting point definition of the epsilon. Okay, so now that we have learned about the epsilon tensor, let me go back and to that previous question that we had. How do we write the curl? Okay, how do we write the curl of a vector field? So the curl of a vector field is given by, so V is the curl of A, and this we can write with the help of this epsilon tensor. Vi I can write as epsilon I j k del j a k. That's the compact expression for the curl. Now let's see. So if I say I want the V1 component, okay, so if I say I want the V1 component, then the epsilon becomes 1 j k del j a k. Okay, now this j and k can at most be 2 and 3. It cannot be 1, because if it is 1 it vanishes, right? So it can be 2 or 3. So let's say if j is 2, then k has to be 3. So that term would be del 2 a3. Okay, and this is equal to 1. And it is also possible that I have j equal to 3 and k equal to 2. But epsilon 1, 3, 2, that's minus 1. So this is going to be minus del 3 a2. Okay, so that is the expression for V1. Let's go back and check what was the expression for V1 in the curl. So when we evaluated the curl here, when we evaluated the curl, where did we do that? Yeah, so this was the expression. So we had, del 2 a3 minus del 3 a2, right? Del 2 a3 and del 3 a2. So this just follows from there. So similarly, the other components, V2 and V3, also follows if you just write out these expressions. Okay, you know what I did here, right? I just took this and wrote this as epsilon 1, 2, 3 del 2 a3. Sorry, I think I can't see that. So let me use this. Yeah. What I did was, I want to write this as epsilon 1, 2, 3 del 2 a3 plus epsilon 1, 3, 2 del 2 a3, del 3 a2. Now this was equal to minus 1 and this was equal to plus 1. So you get this. Okay. So that's how you would deal with these indices. Okay, but our main gain here, using the epsilon, we can write down a very simple expression for the curl of a vector field. Okay, so the curl of the vector field can be written in this way using the epsilon. Now So let's immediately look at some examples of having written this. So let's work out some examples where this definition of using the index or writing the curl in terms of the indices, this can be usefully utilized. So let's write down some example. So if I want to write down some example, let's take this. Okay, let's consider the vector identity, for instance. Okay, let's consider the vector identity. Let's consider. I'm sure all of you know what this vector identity comes out to be. So the divergence of a curl is 0, right? This is equal to 0. Let's see if it follows from, somehow immediately follows when we write this out in our index notation. So the first thing, what we'll write, this first is the divergence of a vector field whose component is, let's say, I. This component is I. So this I can, at first immediately write this, the first thing as something like del I curl of A, this vector, that's I component of that, right? So if I write that, then I will write del I. Now this, I can use the epsilon definition, epsilon I, the ith component of this, epsilon I j k del j a k, right? Now this is equal to simply, again the epsilon is just 1 or 0, so I can bring it out. So this is essentially epsilon ijk del I del j ak. Now those who have seen this before can immediately identify that this goes to 0. You will also be able to identify that this is 0 immediately, because essentially you see what is going on here. This I and j indices, these are antisymmetric, but here they are symmetric. Okay, so here you can interchange them and you get a sign, and here if you interchange them, you will not get a sign. Okay, so that is the idea why it vanishes. But let me spell it out to you, because for some of you this may be the first time. So let me spell it out to you that how this vanishes. So this immediately vanishes, we know. But let's say that there is some quantity. This object is some quantity. So let's say epsilon I j k. We have del I del j a k, and we want to first write, exchange these two. We want to first exchange these two indices. Okay, so if we exchange these two indices, we'll get a sign. We'll write epsilon j I k, but then with a minus sign, because I have interchanged this. I'll write del I del j a k. Okay, this is what I'm going to write. And then this object, I can again interchange the deltas. These derivatives I can interchange now. This derivative I can interchange, and I can write this as minus epsilon j I k del j del I a k. Okay, the derivatives are always interchangeable. Okay, so this I can interchange now. So if I interchange this, I will not get any other sign. Okay, I'll not get any other sign. But notice now, here in the indices, this one is summed with this, and this one is summed with this. Here also, this was the case. This one was summed with this, and this one was summed with this, j's were summed. Okay, so basically here what we can do is we can relabel. So what we can do is, this index, now this index we can call I, because this is a, this is a summed over index. So summed over index we can call anything, So let me just say it. So I can, let's say I want to write a dot product. Let me just explain this point. Let's say I want to dot product v dot a. Okay, v dot a. So this I can write as vi ai. Okay, because I is summed over here. This I can also write as vj aj. Okay, I can write down m and n here, that will also not matter, because whenever there is a repeated index, I can make it anything. Okay, I can make it anything. Okay, whenever there is a repeated index, I can make it anything. So therefore, I can just relabel the index and say that this is epsilon I j k del I del j a k, and as you can see here, this one becomes identical to this one now, okay, but with a minus sign in front. So if something is identical to something minus of itself, there's only one real number that is minus of itself, and that is equal to 0. So from here we can safely conclude that epsilon I j k del I del j a k, this is equal to 0. Okay, and this immediately implies, because this is equal to this immediately implies the divergence of a curl of a vector field that is equal to 0. So you have proved this identity using this index notation. Okay, so that's the first thing. The second thing, let's do another, slightly more complicated identity. So let's take the curl of a curl right now. Okay, curl of a curl, I'm sure you will be able to tell me, all of you, what the value of this curl of a curl is. But let's figure it out, if we can figure it out by doing the computation. Okay, so let's try to do the computation. So the first curl, let me write using the index notation. So this I will write as it. So I'm interested in the ith component of this vector, let's say. So this I is the same thing as this I. Now j, k, this derivative gets the first index j, and then we are remaining inside is this curl of a, that gets the k index. Okay, so now I can take this and then rewrite this. So here I have epsilon I j k del j. Now this one I can rewrite again epsilon k, let's say m n del m a n. Okay, I can write this in this following way just by using the definition of the curl. And again I can pull this epsilon outside. So this is epsilon I j k epsilon k m n and del j del m on a n, right? So now as you can see that there's one index which is common between the epsilon, and it's summed over because it's repeated. So if it is summed over, then I can again take this, I can take this k and shift it here, right? If I do that shifting, then I will not get any sign, right? I'll not get any sign because I'm bringing it across two indices. So I can write this as kij epsilon k m n del j del m a n. Okay, this I can write. Now here this one comes back. We can go back to our product formula that we were talking about before. We can go back to essentially we can go back to this one here, this one. So if we go back to this one, we can see that this I and I is summed over, and then we have these being expressed in terms of the Kronecker deltas. So let's express this expression in terms of the Kronecker deltas. So this one I can write as, therefore, Kronecker delta I m Kronecker delta j n minus Kronecker delta I n delta j n. Okay, this is just equal to this product of the epsilons. The product of the epsilons is just equal to this object. Okay, so now I have the usual del j del m a n. So now you see we have two terms here. So the first term I have to set I equal to m. Okay, I equal to m and j equal to n. Okay, so here I have to put del j del I a j, because I have to put n equal to j. I have just put a equal to j and summed over j. Okay, that's what I have put here, minus I equal to n and j equal to n. So this is del j ai. Okay, so you see what has happened. So can we read off this in terms of the divergences and gradients and divergences? Can we read this off? So you see this, what this tells us is that it is this object. So I can pull, again, take this del I and bring it outside, because I can interchange derivatives always. So I can write this as del I del j aj, but del j aj I know is the divergence of the vector field. So this is nabla acting on the divergence of A. This is this term, and this one, this other term is, here you have a sum over the deltas itself. So this is the actually the nabla square operator or the Laplacian operator acting on the vector field A, because this index I is basically the index I that we started off with. You know, this was the same index as this one, so that will carry the vector index here. So this is so here we will have, and because this is summed over, we have this nabla square here. So this is going to be minus nabla square A vector. So basically this identity we just worked out, this is minus nabla square A vector plus nabla divergence of A vector. So you can just go back to your old books and verify whether this thing that we have derived using this new technology, whether this is correct or not. Okay, so please go back and check whether this is correct. Okay, check this. Okay, so very good. So this is how we are supposed to use this index. I'll give you some more exercises in your assignment, in your first assignment, where you will get some more familiarity with the index. Okay, so before we finish, I want to mention a few more things on vector calculus, again, which you are perhaps familiar with, but I'll just recap, for the sake of, putting everything together once. I'll just mention. So the next thing that I want to mention is basically this divergence theorem, right, or Gauss theorem. So this theorem tells us that if we have the divergence of a vector field, and if we take that and if we integrate it over a volume, okay, let's say dV, this is going to be equal to the vector field dotted with a surface, surface vector, and this is the boundary of V. So let's say this is some volume V, okay. So let's say this is some volume V. Let's say this is some volume V. Okay, this is some volume V. And this boundary surface, this is what I'm calling, this is, so the boundary of V, so this is a standard notation for boundary. So this del, don't confuse this with partial derivative, okay. This is, means that this is the boundary of volume V, okay. So it's a boundary of V, so it's going to be a closed surface. So this is going to be a closed surface. So we have to perform an integral over this closed surface, and here this ds is the surface element on the boundary of V, and its direction is normal to S, it's normal to the surface, pointing outwards. Okay, so that's your divergence theorem. You've all seen this and used this a lot of times, I'm sure. The other thing that we need is the so-called Stokes theorem. Right. So if I take this, now if I take a curl, if I take a curl of a vector field, if I take a curl of a vector field and integrate it over any surface, not necessarily a closed surface, okay, and you know, this is how, let's say, I integrate it, okay, so it's a curl of a vector field through, you know, this surface. This is given by the line integral of the line enclosing this surface, or the boundary of S, again, the boundary of S, A dot dl. Okay, again, this is dl is the line element and del S is the boundary. So now this was really a volume. This was really a volume element like this. This was really a volume element. But now here we literally have a surface, let's say a 2D surface. And so basically there's a line. So this line element here is basically dl. So we have this A dot dl, and so this line which bounds this surface, so inside we have S, and this boundary of this S, you know, the line bounding the S, you know, this is called del S. This I'm referring to as del S. So this integral is again a closed, you know, a closed integral over the boundary where the boundary line element is del L. Okay, that's the other thing that we need, so this, if you are familiar with this, this will be more or less, you know, everything that we would need. Let me end here with a brief remark, which is going to be very important. Okay, I think, you know, there's one property that is common to both the divergence theorem, the Stokes theorem, as well as, you know, this simple fact that you know for ordinary integrals in one dimension. So for ordinary integrals in one dimensions, you know that if I have d dx of some f of x dx, okay, if you integrate this from a to b, then you know that this is going to be equal to f of b minus f of a, right? You know that this is the case. So in all these cases, there's one thing which is common. And this one thing which is common is the fact that a total derivative, whenever you have a total derivative, the integral of a total derivative, so the integral of total derivative is always a boundary term. This is very important. You see here also, because this is a total derivative, so it only depends on the value of capital F at A and B. Here, you know, because this is one dimensional, the boundary are just 2 points, A and B. So this is given by f of b minus f of a. This is, you know, this is just a consequence of this integration. Okay, so essentially if it is a total derivative, then only the boundary values of the function of which it is a total derivative, you know, this integrand, you know, that function, only the boundary values matter. You see, only f of b and f of a matter. Here also, you see, here also this is some kind of a derivative, but this derivative, you know, is acting on this whole function, okay, a, okay. So this derivative this is a total derivative term. Here, because you are in 3 dimensions and you're dealing with vectors, you know, there are many things that can happen, but the essence, you know, remains the same, that the total derivative always gives you something which is determined from the boundary alone. Whenever you have a total derivative and you have an integral over it, then you get back only, you know, terms that are dependent on the boundary alone. So let me, you know, again emphasize one point, very important. So this is even for the divergence theorem, you see, there's a total derivative, and when you integrate it, then you get back only something that is determined from the value of this vector field on the boundary alone. Okay, so you see here this integral, in order to perform this integral, you would have to know you will have to know this A field everywhere in this volume if you want to perform this integral. But if you want to perform this integral, you only have to know the value of A at the boundary. Okay, so if it is a total derivative acting on something, then it is always a boundary term. Similarly here, you see, here if you have to evaluate this integral, then you have to know what this A field is throughout this surface, right? But in this form, you only have to know this A field only on this boundary line bounding the surface, right? So this is again the same feature, that the total derivative, whenever there is a total derivative on something, that can be written as a boundary term. Okay, this is something which I want you to appreciate. So this was the remark, and this also happens in the most trivial case of one dimension. There are also the boundary points, you know, A and B. If we know this f of x function only at A and B, then I can always perform this integral. Okay, so with this, let us end this first lecture, and we will resume with a more physical discussion of the Maxwell's equation from the next lecture.